Hello everyone, let us start lecture 4. And the topic, it is continuation of what we have been discussing for the last 3 lectures. So, it is activation polarization, and concentration polarization, and now we will try to get into mixed potential theory. We have already talked little bit at the end of lecture 3 mixed potential theory. So, we wanted to explain dissolution of zinc in acid medium, which is HCl at some pH, and we could see that the overall reaction would be zinc plus HCl, zinc chloride plus H2. So, this is the overall reaction, and we are trying to explain zinc dissolution or corrosion in HCl, which is pure and deaerated, means no dissolved oxygen. Now, we could also see that the anodic processes and cathodic processes so this is anodic, this is cathodic. Hence, these are electrochemical reactions, and we could also see that separately, if we consider a zinc plate dipped in zinc containing solution, we will have a situation like this situation will get. This is I A, this is I C, and in this way neta A, and this direction neta C, and this point corresponds to I 0 of zinc, or I can just go down little bit, which is I 0 zinc on zinc surface, and this corresponds to E equilibrium or E zinc plus zinc. Now, this value would depend on what is the concentration of zinc ion in that electrolyte. Similarly, for this reaction we can also have similar type of polarization, where this is log I, and if I see the 2 segments, this segment corresponds to I A, which corresponds to this reaction, which is nothing but H minus E equal to H plus, and this part is nothing but H2. So, this is anodic process, this is cathodic process, because both these processes I can have anodic as well as cathodic. So, I can here also I will have E equilibrium, and now here E equilibrium, which is nothing but E H plus H2 E 0 H plus H2, this is we are considering reduction potential, plus RT 2F, because here we are considering 2 electrons, this is 2 electrons. So, now Ln activity of H plus, because there are 2 H plus ion and partial pressure of hydrogen, sorry, this there should be nothing like this, and if I take 25 degrees Celsius temperature, 1 atmosphere pressure. So, then this value is 0 and this becomes 59 by 2 into 2 log H plus, because if it is 1 atmosphere, this is 1 atmosphere, then this becomes minus 0.059 log of H plus, and it can be written as pH, since we know pH equal to minus log of H plus ion concentration. So, now this value will be decided by the pH of that HCl medium. So, this is equilibrium value, and this point is nothing but I0 of hydrogen on zinc surface, because this particular electrode will be constituted like this. You have HCl medium and you have a zinc plate. So, this is zinc. Now, you have hydrogen gas which is flowing in, and this is at 1 atmosphere pressure, this is HCl. So, and we are maintaining H plus ion concentration. If it is 1, then the pH will be 0, and that time E 0 would be, E equilibrium would be E 0 H 2, which is nothing but 0. But if this H plus ion concentration has got some other value other than 1, then it can have equilibrium potential value related to this equation, which is E 2 H plus H 2, fine. And since it is happening on the zinc surface, we are taking a zinc electrode. So, then that hydrogen evolution exchange current density we have to write in the with respect to zinc electrode, that is what this subscript we are taking zinc in the bracketed form zinc. Now, these two situations can have if we have a separate process like zinc dipped in zinc containing solution, and if I consider a hydrogen electrode like this. But once we combine them, okay, so once we have a situation like in an HCl solution with a pH let us say 1, there if I put zinc, pure zinc, then we will have this reaction, these two reaction will start happening. Depending on the concentration of zinc in the when the double layer forms on the zinc surface, that means on the zinc surface we will have a double layer, which is here it will have zinc ion and this is zinc. So, we will have a double layer, and that double layer formation will have IHP, OHP, and then it can also have E equilibrium, which is nothing but E zinc plus plus zinc, depending on the concentration of zinc plus plus ion in the vicinity of that zinc plate. Similarly, that hydrogen will start bubbling on this particular surface, it will also form double layer, and then that will also decide its equilibrium potential depending on the pH value. See, if we combine in a plot, these two plots we are now combining, assuming that the zinc ion concentration we are taking, whatever zinc ion concentration we will experience here. So, that time here we will have E zinc plus zinc, and here we will have E hydrogen H2. These two layers with two levels we will have. Since we already know that E0 zinc plus zinc equal to minus 0.76 around 761 volt, or I can write volt, and E0 H plus H2 equal to 0 volt. So, that means in the potential axis with reference to the hydrogen standard hydrogen electrode, this SHE is nothing but standard electrode SHE, fine. So, with reference to that, this value will be on top of this value if we consider in the standard state of that two partial or the half cell. But since it is not a standard condition, we have some pH 1. So, in this case the potential will not be same as this, or potential would be minus 0.059 pH is nothing but 0.059 volt. And in this case we are not maintaining zinc ion concentration to be 1, rather it is much lower than that. So, these potential value will further go down in this case. So, E equilibrium, which is nothing but E zinc plus zinc, would be less than E0 zinc plus zinc, because zinc ion concentration in the actual system is lower than the unit activity or unit concentration. Now, that case of course their level would be like this, but of course here the value would be decided by what is the concentration that zinc metal is facing in front of it. Now, it will have its own polarization. Individually we will have polarization like this. This value is I0 zinc on zinc surface, and similarly I can have I0 hydrogen on zinc surface. So, this line is nothing but 2H plus 2E equal to H2. This line is 2H minus 2E equal to 2H plus. This is zinc minus 2E equal to zinc plus plus. This is zinc plus 2E equal to zinc. So, this is corresponding to IC of zinc, corresponding to IA of zinc. This is corresponding to IC of hydrogen, this is corresponding to IA of hydrogen, fine. So, these are the current densities we could see. Now, whenever we have a system, two system working in tandem in a particular situation like this, we have to make use of mixed potential theory. We have already explained mixed potential theory at the end of third lecture, saying that there could be a number of cathodic and anodic reactions, and at the same time the system will try to find a mixed potential where the net current density corresponding to cathodic current and the net current density corresponding to anodic current, these two will be similar. So, we will find E mix where I will have summation of IC equal to summation of IA. and of course, I am taking mod, since we have considered IC to be the negative current, it is the direction, not the value. Magnitude wise it is having a finite magnitude, but the direction is opposite to the current IA. And remember, this IA is nothing but the current in the outer circuit, and the IC is the current corresponding to electron flow. Now, let us just analyze this. For example, if we have a cell like this, is let us say copper sulphate solution, this is zinc sulphate solution, and let us say concentration of copper ion is equal to 1, and here zinc ion concentration equal to 1. And then if we have as copper rod and if we have zinc rod in those solution, if we allow them to stabilize, we will develop some potential here, we will develop some potential here. Now, if we connect with the salt bridge, this is salt bridge, and now if we connect them with a conductor, we will see, if we put an ammeter here, we will see that the current is flowing this way. This is the system current, and the electron flows this way. So, now the electron flow corresponds to IC and the current flow corresponds to IA. So, now we could see that the current in the external circuit or the conductor, it flows from positive terminal to the negative terminal, and in the solution it is basically from negative to positive terminal, but the system current is opposite to the electron flow, and the electron flow direction is nothing but the IC. That is the concept. Now, we have to find out, here we could see that there are two reactions, one cathodic and one anodic. Now, it has to reach a situation, a potential which will be between these two potential, and at that potential we could see that the net current density for the cathodic process and the net current density for the anodic process will be similar, and I could see that situation is arriving when they are approaching and intersecting at this point. And here I could see that these IC hydrogen equal to A zinc, and this potential corresponds to E mix, and that is the whole concept of mixed potential theory. Fine. So, this is the potential the system will achieve. Now, coming to some salient features in this diagram. So, this is of course log I scale, because these two plots are done on the basis of log I. So, this is also log I cell, this is potential axis. Now, if we consider this point and this point, 3 points, they are having some unique features. If I consider, let us say I am giving some name, let us say STU. Now, if I could go to, if I talk about S and U, there the potential which is nothing but the non-corroding system. Or non-corroding situation, and I will achieve I0 in case of S. In case of S, it is nothing but hydrogen on zinc surface, and in case of U, it is I0 zinc on zinc surface, this is U. And interestingly, at these 2 points, I could achieve steady state. and forward and backward reactions are equally, the rate of forward and backward reaction at these 2 points are same, and in this case it is basically these 2 reaction, and in this case these 2 reaction, they are happening at a similar rate. Now, coming back to this point, this is an interesting point. This point you see that the IC and IA both are same. Here also you see IC and IA are same. Here also IC and IA are same. This point, these 2 values are same. These 2 values are same. Here also these 2 values are same at this point, but they are corresponding to the same species, zinc, zinc plus plus, and here it is H plus H2. Now, but in this case, though it is IA equal to IC, but they are of different species. In one case it is zinc and here it is hydrogen. So, though here somebody can say that these are 2 rates are similar, because I is nothing but the rate of the process, that means rate of the cathodic reaction is similar to the rate of anodic process. Here also the rate of cathodic reaction and rate of anodic reaction both are same, but in this case there are different species, then that means we cannot say that this point is an equilibrium position, but we can say that the rate at which zinc dissolution is taking place is steady. That means it is happening at the same potential all throughout. Of course, it is an open system, that means hydrogen is continuously going out, and that is what the reaction is continuously taking place at that particular rate. So, this condition is it's, though we can say that the rate is fixed, but it is not equilibrium, but here the rate is fixed, but it is equilibrium. Now, coming to further, just to add it to this particular thing. So, here I can say this is nothing but I core of zinc. Why? This is IA is nothing but the dissolution of zinc in the form of zinc ion. So, that is what it becomes, the corrosion current density of zinc in HCl of pH 1. So, this is the connection between activation polarization and mixed potential theory, because both the cases we are actually expressing all the lines, this line, this line, this line, all 4 lines we are expressing with the general expression beta log of I plus some constant C. So, this is nothing but Tafel equation, and the Tafel equation is valid in the case of activation polarization. Fine. So, this is the connection between activation polarization and mixed potential theory for a simple system. Now, there will be one more important aspect of polarization, which is called concentration polarization. Fine. So, let us look into this part. Now, when we considered activation polarization, we have considered this is IHP, OHP, we have considered atomic jump from one end to another, this is Mn plus M, and if IA is more than that, so this will be the distribution of energy, free energies. So, this becomes my over voltage, and if it is A, B, C, so A B by AC equal to alpha, which is symmetry factor. So, that means this particular case, and in this case IA greater than IC for the dotted case, for the dotted line, and this is the corresponding situation for I0 equal to I c equal to I a. Now, in this case if I look at, it is basically the thermally activated jump process, and it happens at a smaller current density level, and the basic assumption is when this happens, the concentration at this particular end does not change. So, if the concentration here is C0 in the beginning, so the C0 concentration remains there, okay, with the polarization. But if we go to a higher and higher current density, that means if we switch to higher and higher level of polarization, then I would have a different situation. Okay. So, now even if it is for I a and I c, for if I do it for I c greater than I a, so that case the plot will be like this, right. This is the green color for situation I c greater than I a. Okay. So, if we go to a higher polarization, so that means over voltage becomes very high, those situations C0 at OHP will change, and that lead to another kind of polarization, we call it concentration polarization. Fine. So, let us stop here. We will continue our discussion on concentration polarization and its relation, its interaction with the mixed potential theory. Thank you.